Let's talk about algorithms now. Three goals for today. First of all, refine a concept of an algorithm for computational problems. Second, motivate ourselves to do some algorithm analysis and to study more algorithm analytic tools. And finally, we want to answer the questions, why should everyone study algorithms? So what is an algorithm? Algorithm is any step-by-step procedure for solving a particular problem. Here's an example of a cooking algorithm. The algorithm for making an omelette. There are algorithms for solving puzzles, or even algorithm for improving our mood and well-being. The word algorithm comes from the name of Persian mathematician Al-Khwarizmi, and in his work, algorithm meant a precise and unambiguous sequence of instructions that lead us to a desired result in a finite number of steps. The algorithms here are intended for solving a mathematical problem. An algorithm for solving a computational problem is a precise and unambiguous sequence of instructions that convert an input into a desired output in a finite number of steps. Important words here are precise and unambiguous and finite number of steps. So here is an example. I will teach you how to add 328 and 94. First, add up the ones. Write down 2 and remember 1. Now add tens plus 1 carry over. That makes 12 tens. Write down 2 and carry over 1. There are 3 hundreds plus 1 carry over. That makes 4 hundreds. The result is 422. Technically, this algorithm has finite number of steps, and the steps are very precise and unambiguous. However, this is not exactly an algorithm we are interested in, because this particular sequence of steps shows us how to solve an instance of a problem, an instance of a more general problem of adding multi-digit numbers. So here is an algorithm for solving a general problem of adding multi-digit numbers. We will adjust our definition of a computational algorithm slightly. Computing algorithm is a precise and unambiguous sequence of instructions that converts an input into a desired output in a finite number of steps and that solves a general problem and not just a problem instance. Such algorithms can be translated into a sequence of precise machine instructions and be handed over to a computer to execute. Each computational algorithm is a sequence of instructions for converting a given input into a desired output. Thus, to formalize a computational problem, we need to answer what is an input and what is a desired output. In the first example, the input is an array of integers and the output is a median, that is the middle value after all elements of array A are sorted. In the second example, the input is an array of integers and the integer t, and the output is the index of the first occurrence of t in A. Every program you have ever written is an algorithm. There are, however, algorithms with straightforward and already efficient solutions that cannot be improved no matter what you do. As an example, consider searching for a given word in a raw text. So we just need to scan the text and compare each word to a given word. Or for example, counting total number of characters in the string. We assume that you already know how to solve these computational problems, and these are not the algorithms that we will study in this course. In this particular course, we are interested in algorithms with clearly defined inputs and outputs that need non-trivial ideas or data structures to operate efficiently. As an example, consider sorting. Many different algorithms exist for converting a raw array of numbers into a sorted array of numbers, and these algorithms differ in their efficiency, and we need some non-trivial approaches in order to be more efficient. Another example is to find out if the arrangement of parentheses is valid. As you can see, this is a non-trivial problem because just counting the number of opening and closing parentheses will not make the trick. These are the algorithms we study in this course. And of course, there are some computational problems which are much more complex than the problems we will address in this course, such as, for example, identifying objects in photographs or understanding natural language. These are algorithms which are studied in AI or machine learning courses, and they differ in a sense that there is no clearly defined input and output. To solve such problems, we need first to break the big problem into sub-problems, and for each sub-problem, invent an efficient algorithm or maybe even an heuristic. So these are not algorithms that we are going to study in this course. Now let's talk about comparing algorithmic solutions to the same problem. Let's say you have a task of going from city A to city B. There are many ways of doing that: by flight, by bus, by car, by train, or by bicycle. All these solutions differ by cost and speed. The same applies for algorithms. We want to know which solution is the cheapest, consumes less computing space, and which one is the fastest, produces results in less time.
To understand that we currently do not have the tools to predict the performance by looking at the code, let's again go to the demo of our previous program, which was counting the most frequent words in the list of words. So here is our naive solution, which goes through each word in the list, and for each such word goes again in another loop to see if there are some other words which match the current word in order to increment the count. Compare this code with the code which uses a hash map. If we look at these two implementations of the solution, we see that here we have the nested for loop. That means for each element of the list, we perform another iteration through the same list for each another one. And here we only iterate over the list of words once. So maybe if we replace this inner loop with a single Java command, that will improve the performance of this algorithm. So we going to use our friend, which is the Google search, and we ask, how to compute frequency of an item in a list in Java? The most straightforward and recommended method for its conciseness and efficiency is collections.frequency. So this is how we compute the frequency of a single word in the list without iterating over the list. All we need to do is to write collections.frequency, pass it a list, and the word that frequency we are looking for. Okay, so we implemented this solution in this different variation of this list. See here, there is no more the inner loop. There is only collections.frequency all. And finally, of course, for completeness of this, let's add the fourth variation of the solution, which is going to be the solution generated by ChatGPT. So see, here we asked, write me a Java program that finds the most frequent word in the list of words. So here we also use something very similar to what we use in our program. See, we actually use the hash map. So this program looks very similar to the program that we created. Both the AI program and our program, our fast program, uses hash map. See, there is no difference. And let's now try to predict how these programs, these four programs, will be ranked by their performance. Okay, we already know that the most frequent is very slow. However, we hope that most frequent, which uses the Java built-in method, will be faster because there is no an inner loop here, right? And we also kind of hope that the AI found us the best solution of all. So we will first try to run it on this input file, which contains 33,000 words only. So we are going just to run it and see the results. Okay, it took 4 seconds to the most naive method. It took more than twice that much by using the frequency method of the Java collections class. It took only 22 milliseconds by the solution proposed by ChatGPT. However, our solution is even slightly faster than the one that proposed by ChatGPT. So it is not immediately clear to you why that happens. So it seems that just by counting the number of Java instructions, it's not enough to predict the performance of the algorithm. This is one conclusion from this experiment. And the second very important thing is, as you can see here, the best solution differs from the worst solution in about 1,000 times. 1,000 times this is faster than this. Now the question is, if we triple the input to this program, what would happen if we just take the file where there are approximately 3 times more words than in this one? Would those variants also, would those running times also triple? See? So that would take us too much time to run here, but we can look at the results of the run and we can see the following things: that the worst possible solution, which uses Java frequency method of collections class, runs in more than 2 minutes, whereas our Java hash map still at 25 milliseconds. So it seems that it's much more than tripled the number, here the running time. And also now our best solution is not 1,000 times better than the worst one, but how many times? Many more times better than the worst one. So this example demonstrates the need for real tools that will allow us to analyze our program performance and compare our solutions by their efficiency without ever implementing the solutions. And that will be the topic of the second part of this course.
So, we want to acquire analytic tools to be able to answer the following questions. Which algorithm is better? And we want to know that before we implement the algorithm. How will the running time change for different inputs? How will the running time grow if we increase the input size? Will we have enough memory to run the algorithm on large inputs? And we will be able to answer all these questions after part 3 of this course, where we will delve into analysis of algorithmic running time. Here I just wanted to share with you some ideas. So how do we know which algorithm is faster? Can we just count the number of statements for the machine to execute? There are some problems with this approach. Because, for example, if you look at comparing two strings and comparing two integers, these two statements do not take the same amount of time. because the strings can be very long and we need to compare them character by character. The idea is to express the running time of a given algorithm as a function of the input size, and then compare these different functions mathematically. For example, if the running time depends on the input as n cube, this will take more time than the algorithm which takes n square steps, especially when n becomes really big. We will learn how to derive such functions and how to use them to predict the performance of our algorithms. And finally, let's talk a little bit about why do we want to study algorithms. Now, first of all, if you want to become proficient in computer science, in any area of computer science, you need the mastery of algorithms. Secondly, exposing your brain to new ideas and concepts is good for brain development. The third reason is that inventing and studying algorithms is a fun and addictive activity. Finally, after this course, you will appreciate all the creativity that different people put into developing algorithms and how much these algorithms changed the modern world. Here are some examples of these algorithms that changed the face of the modern world. Google search, for example, would not be possible without the PageRank algorithm. You would never be able to withdraw cash from a banking machine without invention of concurrent transactions. Nobody would be able to issue online payments without inventing an algorithm of public key cryptography. Error correcting codes are used for reliable communication. And finally, the shortest path algorithms are used for GPS systems which find you the shortest path from your start to the destination. In fact, it's believed that everything in the world is functioning according to some algorithms. Even living systems are just machines that execute algorithms on biochemical hardware. You might disagree, of course,